Hi everyone, welcome to week 7, lecture 2 for Blue Planet. My name's Luigi Renzula. I'm going to talk today about the distributions of moisture and heat in the atmosphere and how they can lead to weather. I'll cover topics such as air mass and what happens when air masses meet and create fronts, and how those fronts can lead to precipitation. And finally, how these air masses move around the planet under the pressure variations of the Earth's surface. You've seen this animation before. It's precipitable water. It's estimated hourly over quite a long period of time, actually, if I let this animation run. But what I'm using it here is to highlight what we know about the intense solar heating the Earth receives at the equator. That intense solar heating heats the surface, which in turn heats the air above it. The overlying air in the tropics is warm, and warm air, as you recall, can hold a lot more moisture than cold air. So because there's a lot of moisture to evaporate in that region, we tend to see a lot more moisture in the atmosphere than in other parts of the globe where the air temperature may be cooler. The reason I highlight that is because it illustrates quite nicely this concept that the atmosphere will tend to take on the characteristics of the underlying surface, and that leads to what meteorologists call the development of air masses. So these are bodies of air with horizontally uniform property, and we classify them with two letters. The first letter corresponds to its moisture content and its source, the moisture source, if you like. Whether it's maritime or continental. They can be moist. In maritime air is moist and has a typical high relative humidity. Continental air masses, however, are typically dry and have a low relative humidity. You recall the big driving force for Australian weather is that high pressure belt across most of Australia. The Hadley cell, the descending arm of the Hadley cell called the subtropical ridge, those high pressure systems bringing cold, depleted air into the middle of Australia, moisture depleted air into the middle of Australia. So the drier continental experience there. The second letter of the air mass classification corresponds to the temperature. So just broadly categorized as the equatorial region, the tropics, the polar region, and the Antarctic. And of course, the equatorial region is the hottest. That's where we get that greatest concentration of solar radiation. And the famous line in our national anthem, Australia's national anthem, is "Australia is girt by sea." We get all our moisture or all our weather because we are surrounded by ocean. We're a large land mass surrounded by ocean. And so we have air masses. In the centre of Australia, of course, shouldn't be too surprising, we have the continental tropical air mass. From the northeast, we get contributions from the tropics. We get maritime equatorial air mass. From the Indian Ocean, we have the air mass, maritime tropical air mass. From the polar region, we have the maritime polar air mass from the Pacific and Southern Oceans. And then from on the eastern side of Australia, we have the maritime influences of the tropical air mass from the Pacific and tropical air mass from the Tasman Sea. So when these air masses encounter the continental air mass, that forms the weather we experience. There's a nice animation to show that idea. We've talked about this before, but I think this graphic shows it nicely. What you have in red there is warm air, and blue you've got cooler air. We recall that cooler air is more dense and it displaces the warmer, less dense air. So cold air displaces the warm air. Cold air is more dense than warm, so the higher density fluid move under a less dense fluid. And in lifting up that warm air, creating convergence of airflows. When we have a polar air mass, for example, encountering the continental tropical air mass, so the polar air mass is maritime, so it's moist, and it's from the polar region, so it's cool. Whereas the continental air mass is warm and dry. When those two air masses meet, you have a cold moving air mass encountering a warmer mass. You have the lifting of that warm air by what's called a cold front. Rapidly moving cold, dense air slides underneath the slower moving warm air. The warm air rises and can lead to heavy rainfall or snow, depending on how much moisture is in the atmosphere, but also how quickly that warm air is lifted. Alternatively, you have a warm front. This is like an example where the continental air mass moving into the maritime polar air mass. You have a rapidly moving warm air mass catching up to a slower moving cold air mass. That warm air mass, being less dense, will gradually rise over the cold air mass. So it's not as rapid a lifting as when a cold front comes through, but nevertheless, the warm air lifts over the top of the cold air mass and also can lead to rainfall depending on how much moisture and how quickly it's lifted. Rising moist air eventually leads to precipitation. When warm fronts and cold fronts meet, the warm air rises above the cool air, and through our ideal gas laws, we can see what might happen there. So remember that as you move up the atmosphere, both temperature and pressure decrease with altitude. So you have a warm, typically moist air mass lifting into the atmosphere where both pressure and temperature decrease. That means the moisture that's in the air, in that warm air, slowly starts to, the humidity starts to increase. And when the temperature drops to dew point, you start to get condensation. So cool air can't hold as much water as warm air. Remember, through that saturation vapor pressure relationship, you see that this graph on the right is the function of saturation vapor pressure as a function of air. And for any given air parcel, it has a vapor pressure. We compare that to the maximum vapor pressure it could exert at saturation to get our estimate of relative humidity. Cooler air molecules have less energy than warmer air molecules. And so what ends up happening as the temperature decreases, that we transition from a gas into a liquid. And that liquid eventually comes out of the air to form clouds. And if it lifts enough, it will lead to rainfall or precipitation.